Hello, everybody.
Hello.
Oh,
Hello.
can't see the cameras. I can't see April. How are you, April? I see Perez, Noah, Patrick, one by one. How's everything with finals? Are you guys in the final weeks? Final exam?
I think that technically starts next week on Wednesday.
Yeah, I think next week.
So next week on Wednesday,
Somewhere
28th.
around there.
So you're gonna have a couple of days to study, and then, or the final days exactly start on the 28th. So you're gonna have the exams on 28th, correct?
No.
Do we have like that last day of class is May 11th?
I believe you have at least 2 weeks before the final exams. That's what I
Yeah.
believe. Okay, that's gonna give us some time, and I made it clear on my previous email. It's gonna be a take-home exam, which will be convenient for you and some of you guys staying at the dorms. I received a couple of emails that they were planning on leaving early, and they were asking about the exam, if it's gonna be take-home or online or in class. So to make it convenient for everybody, including myself, I made it take-home. You'll be given a number of questions similar to midterm. Let me see, I'm recording this first. Yes, it's being recorded. Okay. Let me show you first how it's gonna look like. So Moodle, about page. There you go. This is you. There you go. So last year it was take home. So I'm gonna go to the final exam section. Okay, this was previous year. You will have 8 questions. You will receive a PDF file that will include all the questions. You need to print out the PDF and then solve the problems. Then either do scan the paper or take a picture, make a PDF and send it back to me. It's gonna be the format PDF and single PDF. I don't want to have a couple of more different PDFs for each page. It's not going to be long exam, so it's not going to be more than 3-4 pages. I haven't made the final yet, but I know what type of question that you will see on the final, and we're going to talk about those questions and the remaining labs, beam bending and column buckling. So let's go to Moodle first, and I will explain the updates on Moodle, which I made it today. This is the beam bending section. I started the beam bending last week at the end of the lecture. And I will go over again and I will start from scratch and work out a problem. We're going to calculate deflection based on the applied loads during the experiments. And I believe so far you guys already watched the video on Moodle experiment video. I mentioned that video and I even showed it in the class, how we conduct the experiments. And I have the data today, and we're gonna work with this data on the spreadsheet as well as on hard copy. There are additional videos that is helpful, especially for the mechanics of materials lecture. Before the final, you should take a look at these videos, short videos. And you have the beam bending handout here. This is the one that we were going over last week. I will also share this sample calculations. I will go over this and I will update that this PDF, which is a solution of the problem that we're
What
gonna.
is, which one is that for? Is that for the
Beam bending?
beams?
Yes. We will start soon. So I'm just waiting for, oh, it's 5:30 already. Yeah. We can start. Let me see how many people we have. Yes, we have good attendance. Okay. Go back to Moodle. You also have the column buckling section. I'm not gonna assign a lab report on this beam bending, column buckling, wire tensile. I will just assign a problem. It will be similar to one that I'm gonna be working on today. And you will submit 1 or 2 page, depending on your solution. You will provide the answer for the problem that will be assigned on the beam bending and the column buckling.
Those will be the only two plus the wire tensile test.
This is wire tensile test. It will be bonus. So if you want to get bonus points, you can also go through this section, wire tensile, read the notes, and ask me questions if you have any questions, and I'll help you out how to finish this assignment. But this is not mandatory. We also have 2 videos that's going to help you to develop your graphs, histogram, and the bell curve.
I have one more question. I'm sorry.
Mhm.
So the beam bending and the coupling are only going to be on the final. Is that
Mm.
correct?
Final is going to be comprehensive, but you will have questions on beam bending and column buckling.
Right. Like everything, including that, since
Everything
we're not
included in-
doing the labs.
Yes, but we are not going to include the wire tensile test on final. So everything but the wire tensile. Majority of the questions are going to come from concrete, compression test, torsion, maybe tensile test. Definitely you're going to have 1 question on column buckling, and you will have 1 more question on beam bending. And I also have videos on column buckling where I solve the problem with the column buckling theory. Take a look at these videos and expect a similar problem on the final. I believe in midterm I asked the question on torsion, and the similar problem or the same problem was on the Moodle or on my channel. So far this is the updates on the Moodle. Yeah.
I'm sorry. That was for the momentum equation where the you had to take a beam connect to a wall. Was it that specific equation, or I mean
Talking about the midterm question?
question?
Are you talking about the midterm question?
Yeah,
I can-
yeah, that we just had. I'm sorry. I gotta press the space bar to talk to you.
Okay. So in the midterm, it was a torsion problem, and you were dealing with Poland moment of inertia. And the question was asking for the maximum shear stress at the given shaft that is attached to the wall. That was the problem statement. And you will see what kind of question that you might see on the final after I cover the column buckling and beam bending today. And next week, since we still have 1 more week, I will work on column buckling again next week. But I'm planning on covering everything this week, just in case. Even if you have to go, if you have another class after a certain time, after 1 hour, you can just leave I will keep recording the video and share it. All right. So, go ahead, Austin.
I'm sorry, Dr. Tanel. I'm just, I want to clarify everything. So, we're gonna go over the beam bending and the coupling, stuff, but we're not
Column
gonna have,
buckling.
huh?
Column buckling.
Column buckling. Oh, yeah. I'm sorry. And, we're gonna go over those two, but we're not gonna have the labs for those, but we will have them on the final, right?
Yes.
Okay, and then the wired tensile test is not on the final, and that would
No.
actually be a lab.
Yes, it's not gonna be on the final.
Okay, but it will be a lab, correct?
That will be an assignment,
Oh,
but
okay.
it will not be mandatory. It will be help. It will basically it will help you to get a bonus point that will go towards your final grade.
Okay, how many points would that be if we did that?
5 points.
Oh, 5. Okay, all right. I'm sorry. I'm having trouble trying to hear you.
Yes, it is. If you look at the Moodle, you'll see that you can receive 5 extra points, bonus points towards your overall grade. So if you're at 75 at the end of the semester, it will be 80, and you will get a B. But I don't. Everybody is right now at the A range, so I don't think.
What
somebody-
about the bonus points? I remember you said that you would give us some bonus points for like the 5 remaining kids that
If
stayed for the
you
first class.
shoot an email, basically, if you're concerned about your grade after the final, we can have a Zoom meeting, phone call, and then we can continue looking over your bonus points if you receive any, and if I promise any, or we can go over your reports, any sort of issue.
Okay,
So
because
you will have a timeline before I enter the grade. I usually wait till the last day. So after you take the final, we can have a conversation. That's what I do usually.
okay, so after the final or before?
After the final.
Okay, because I remember you want us to do that same problem that I was talking about.
I can hear you right now, Austin. Let's cover this actually after the class.
Okay. Okay.
Let me start the lecture and then we can talk. All right.
I'm sorry about that.
That's all right.
I keep forgetting to press the space bar.
Okay, I'm gonna start from scratch for those of you who wasn't in the class last week or who didn't watch the video. In the beam banding, we are looking at the aluminum beam that is 18-inch long. The span length is 18 inches. And there are 2 loading points on this beam. You see the center line, and since this beam is symmetric, each side, left and right, is 9 inches. And you have 2 support locations. It's simply supported beam. And we have 3 different loading scenarios: 150 pounds, 300 pounds, and 450 pounds. I'm gonna bring up that video again from Moodle, where we run the experiments. This is the beam that you see on the handout. So you have 2 loading points. This is the point 1. I don't know if you can see if my marker is highlighting the section, but this is the first loading point. We're using the hydraulic jack to apply load, and this is the second loading point. We have 1, 2, 3 gauges in this rig, and we're measuring the deflection at 3 different points. One in the center line, in the middle, and second one is 4-inch from the left hand, and the other one on the right side is 6 inches from the right hand. So our goal is to measure the deflection at these 3 locations when we applied 100 50 pounds, 300 pounds, and 450 pounds. So also this equipment right here, this is the strain gauge device. It has gauge, electronic gauge, and it tells me what is the deformation at the bottom of the beam. So I use the strain gauge information to calculate the Young's modulus of the beam. So every time when I run the loading scenario, let's say we start with 150. First, I zero my gauge. Make sure everything is zero. And then I zero the strain gauge as well. And then I'm setting up the hydraulic pump. Starting from zero, it's gonna load the beam up to 150 pounds. If I'm loading with 150 pounds, this beam should experience 75 pounds of load at this section, at this loading point, and 75 right here. And let's look at the handout and compare it. To the same beam, two support at both ends. And this is the first location, P over 2, 150 divided by 2, so 75 pounds of load is applied at this point. And then you have another point, loading point on the left side. That will be 75 as well. Right here, delta 6. This is your deformation at 6 inch from left end. And delta 4 is the deformation at 4 inch. So basically, since this beam is symmetric, deformation at 4 inch on left end will be equal to deformation at 4 inch from the other end as well. Is due to symmetry. Again, the gauge in the middle center line, this one right here on the screen, if you look at this gauge on top, this is going to tell me what is the deformation, what is the deflection in the middle. And when you think about it, Noah, what do you think, which deflection will be higher? 6 inch, 4 inch, or 9 inch? At which point deflection will be higher?
9.
9, right? Correct. So deflection is maximum in the middle. Always get a ruler, something you can bend, and start applying a load. And you will see the deflection is at maximum in the middle, if it's simply supported. I'm sure I showed you guys this setup before when we were in class during concrete mixing day.
Yes.
Right, I showed it before. So after I apply the load is staying at 150. If you look at the gauge coming from the hydraulic pump, and I'm taking the readings. And that's the last reading that I'm taking from the center line, from middle. And those readings, I will also share this spreadsheet on Moodle. Table 1 is the observed data. And let's go over the observed data and how to record it and what they actually mean. Also compare this table with the table that you see on the handout, this table.
So we don't have to do that lab, correct?
No,
Just to clar-
but
just
you
to
will have
clarify.
to, you will have to provide the calculations, and I will get there.
Okay.
When I say calculations, for example, if the loading case is 300 pounds, I will ask you to calculate the deflection at delta 9, delta 6, delta 4 manually. And then you will compare those numbers with the measured deformation. Or deflection.
Okay. All right,
So
thank you.
Experiment is gonna give you the deflection based on the applied 150 pounds. I apply 150 pounds and I'm measuring the deflection at 4-inch, 9-inch, and 6-inch, right? And also, I can use these equations that's also on the handout. I can use the equation to calculate the deflection, maximum deflection, or deflection at any point. So your job is to compare the experimental value with the calculated value. Are we clear on this?
Yes, sir.
Okay.
Yes, we are.
Okay. Let me actually get a water. Give me 1 second. I'm gonna be right back. I have to get a water. All right, sorry about that. It is getting hot over here. I live on North Shore, Vanderbilt. And I have an office in my garage, and today it's been hot, actually.
No, I feel so sorry for you.
Yeah. Thank you. Okay. Let's see. So you watched the first part, the first loading scenario, 150 pounds. And first measurement that I took, actually, it was from the strain gauge from that device, from this device. Basically, that device is connected with a sensor, and that sensor goes underneath the beam, right? When you actually apply a load, the beam is deflecting. Also, it is deforming at the bottom. Correct? So we have to measure the deformation at the bottom. And this strain gauge is giving us that deformation. So I get that
Reese-
value. Yes.
I'm sorry. Are we supposed to do like a hole punch inside of where the two forces go?
When you say punch a hole, what do you mean? I can't hear you, Austin.
I'm sorry. I'm saying as in like if you have a tin roof and you don't want to like knock it, you know, like you have a nail, for instance, and you take a hammer and you kind of knock it just a little bit, and then you can put your screw in there and, you know, the washer in order for the tin roof not to leak. Is that the same kind of deal that we're doing here, where we have to do a hole punch in order for it to be able to catch instead of like shooting out, you know?
No. It's totally different. No,
It's totally controlled. Okay, I just wanted to
no,
ask.
this one is basically it's like a sticker. You place it under the beam. It's like a sticker. Like a sticker. You place it under the beam, and it has the small tiny wires inside, and the wires are deforming, and that deformation is measured by the strain gauge, and that those signals are converted to the strain value. That's what happens. So you're not actually screwing anything.
Okay, thank you so much.
You're welcome. So let's go back to spreadsheet. Right. So I got my first measurement. I know what is the strain at the bottom of the beam. That's 481 micro inch. So we will convert that to strain later. I will give you the conversion unit. And the second column is delta 9, deflection in the middle. So when I apply 150 pounds, I observed 0.024 inches deflection in the middle, which is the highest deflection. Delta 6 is the 6 inches from the right end. The formation was 0.22 inches, and at delta 4 it was 0.016 inches. Okay, and I do the same thing for 300 pounds. If you have watched the video, or if you skip fast forward, you will see that I repeat the same step, and I just increase the load to 300 and 450. So at the end of the experiment, I have my table. I know what are the deflections with the given loading scenario at 3 different locations. Now my job is to use the conjugate beam method to calculate the deflection actually with the given loading scenario and the beam cross section and the beam length. So how are we gonna do that? Let's go back to handout. I went over the equations, but I will go over the equations again one more time. This is the first equation that you will use. Actually, second after moment of inertia. Moment of inertia, since this is rectangular cross section, is BH cubed over 12. B is the base, 0.5, and H is 1.25, which is the height or the depth, whatever you name it. So BH cubed over 12 is giving you 0.08, 14 inch to the fourth moment of inertia. In this handout, you can also see the beam's cross section and the bending axis, and you also see the C value, which is the distance from the bending axis or neutral axis to the top fiber of the beam. It's 0.625. This is basically the half of the 1.25 overall depth. And then second equation is the maximum bending stress. If you want to get more information about these equations, go back to the Moodle, and you will see these external video links. You will see 10 minutes short videos explaining the bending stress and moment of inertia and deflection. So maximum bending stress can be calculated with the maximum moment on the beam. After you draw the shear diagram and the moment diagram, you will take the maximum moment with a loading case of 150, for example, and moments multiplied by C, which is the distance from the neutral axis to the top fiber, divided by the moment of inertia. That's going to give you the maximum bending stress. And you might think that why we are calculating for bending moment or bending stress, because we're going to use that bending stress to calculate the Young's modulus, which we will use later. And you have the strain over here, and that strain value is coming from the experiment that we measured with each loading case, 481. So we have 3 equations. That should be easy, huh? Let's see. But we also should know the conjugate beam method and how we can use the conjugate beam method to calculate the deflection. So these are the assumptions that we are making when we are using the conjugate beam method. For a simple span, the conjugate beam is the same as the real beam. So we are looking at the simple span beam, simply supported, and the conjugate beam is going to be the same in dimensions, but it will be virtual. So we will deal with the virtual beam, and we will make some assumptions by using the original data. load the conjugate beam in second step with the M/EI diagram. And I will show you the diagram we will go over, and you'll see how to develop that diagram. So that diagram is going to be from the real beam and the real loading. We will use the real beam scenario, same dimensions, same span length, same cross section, and with the same loading scenario. Shears in the conjugate beam corresponds to rotation in the real beam, and the moments in the conjugate beam corresponds to deflection in the real beam. That's the most important part because we are trying to solve for the deflection, correct? April, let me ask you this. Can you hear me?
I can hear you. Can you hear me?
Yes,
sir.
Okay.
Can
So,
you hear me?
yes, I can. Yes, I can.
Okay.
Okay, my question is, what are we trying to do with the conjugate beam method? Why are we making these assumptions, and what is our goal?
You said the conjugate, what?
Conjugate beam method. This methodology, conjugate beam, we are using the conjugate beam method to calculate the deflection. So what I said at the beginning, we will compare the measured deflection with the calculated deflection. Right now, we have the observed data. We know deflection at the center, at delta 9, delta 6, and delta 4. And we are trying to calculate the deflection with the equations, with the conjugate beam method, and then we will compare these numbers to see if the conjugate beam method is actually working and giving us the accurate data, correct? Does that make sense?
So we're using it does. It does. So we're using a conjugate method to find the slope.
Yes, you
we trying-
you can find the slope, and you can also find, most importantly,
The
you can find the displacement deflection. That's what we are trying to do in this lab. So conjugate beam method is going to give you the slope or rotation. It can also give you the deflection. So we are after deflection. But whatever is the moment in the conjugate beam, it will be the deflection in the real beam. So at the end of your calculation, you will check the moment on the conjugate beam at 9" in the middle. That moment is going to be your deflection. And the numbers should be close. And it will be close, you will see, in 3 different scenarios. I will go over actually 2. One is this one. It's already on this handout. This is a little complicated, but it will be more clear when I start working on this PDF. These are the calculations that we're going to perform to get the deflection and then compare it with the observed deflection. So we didn't finish the part 4. In this parentheses, it says compare these deflections to those measured and compute the percent error. So at the end of the conjugate beam, you will compare the deflection to those measured in the experiment. That's our goal. And you will compute the percent error. So in this sample, we are using 450-pound loading case because you can tell that 225 is the half of the 450, correct?
Yes, sir.
Okay. 450, 300, and 150. First thing first, you will have the free body diagram. If you want to work out, take out a pen and paper so you can work out the number. So 225, you can, without even using the calculator or pen and paper, you can tell, since this is simply supported and have 2 reaction forces, it will be equal and opposite of the applied forces, right? So summation of the forces on the y-axis should be 0. So if we have 450 going down, you're gonna have 450 going up. Correct? And reaction A is gonna be equal to reaction B because it is symmetrical. So once you get the free-body diagram and calculate the reaction forces, second, you will draw the shear diagram. It's denoted with V on the left side of the screen. Everybody can see this shear diagram? Mohsen, can you see it?
Me? Yes, sir. Absolutely.
Okay,
That's
so
static. That's statics, right?
yes, it's nice. Exactly. This is this
I- Yeah, I had that with you.
first part is easy. And then you're gonna get the shear diagram. So if you have 225 pounds positive going upwards, you will have your 225 plus, and you look in the section at 7.5. This is the distance from left end to the first loading point. There is no force applied in this section, right? So your shear diagram is gonna stay at 225. And when you come to here at 7.5 inches, you have a drop. And that drop is 225 pounds is applied on the opposite direction. So you will have zero shear right at this location.
That's exactly at 0, right? Or
Exactly at zero.
for B going across right there,
So you go 225 up,
right?
there's no force applied at the
Yeah, and then
7.5 section, and then you have 225 going down. So 225 minus 225 is zero, correct?
okay, yeah, it just shows that it's got a little bit
Right,
above the
right.
x-axis, and that's
I realized that, but this is not my handout. This handout is the old one. It was used by different instructors. I'm still using it, but it's just the way that they draw the shear diagram. But if you do
Yeah.
the calculations, you will see that the shear force is zero in that
okay.
middle portion.
You probably would have did it better too, anyways.
Yeah, I will show it to you on the other one. Again, this is not mine, but this one is more clear.
I have
But I
a,
will- Yes, go ahead.
where are the numbers that we're gonna use for when we actually solve this and make the handout?
I'll give you the numbers. Right now, I'm gonna go with 450 pound loading case, and then I will go with 300 pound, and I will assign 150.
Are you gonna give us that paper right there that you're showing us now, the beam bending?
Yes,
Okay. Thank you.
you're welcome. Rami,
And the distances?
so the distances, I will ask you to calculate deflection at delta 6, delta 9, and delta 4 with the loading case scenario of 150 pounds. So instead of using 450 that I'm going over right now, I'm not gonna ask you the same thing because otherwise you're gonna be copying the same work that I perform here. I will give you 150 pounds. So it will be 75, 75. And reaction force will be 75, 75. And you will get the deflection at the end of your calculation in delta 6, delta 9, and delta 4. And you will compare those with these three numbers, delta 9, delta 6, and delta 4. Because 150 pound observed data, observed deflection with 150 pound of load was 0.024 for delta 9, 0.022 for delta 6, and 0.16 for delta 4.
Bless
Okay,
you.
thank
Yes. Is that answers your question?
you. Yes, sir.
Okay. So let's continue. Okay. So we are done with no, we're not done. We had last portion. So we know that in the middle portion, we have zero shear. At this point, we have another 225 going down, right? That's going to be negative shear. So you have negative shear on the right end, on the last portion of your shear diagrams, up until you get to a support reaction 225. That's gonna bring it to 0, and it will close the gap. Otherwise, if this diagram is not closed and you still have a shear force left over, then something is wrong with your calculation. This one is basically summation of the forces on y-axis. So once you get the shear diagram, it will be easy for you to calculate the moment diagram using the shear diagram. Okay. So to calculate the moment diagram, you will use these rectangles, because moment is the force times distance, right? So at this point, I have 225 pounds applied, and I'm gonna look at the distance, 7.5. And if I multiply 225 by 7.5, it will give me the moment at 7.5 inches along this beam. And if I multiply 225 by 9, it will give me the moment at the center. So I'm going to use this rectangle, 7.5 multiplied by 225. That's 1,688 inch-pounds. That is my maximum moment. Over here in the middle portion, since there is no shear force, there is no change in the moment. Since you have a negative shear on the last portion, you have negative moment, and that's closing the gap. You have 1,688 inch-pound plus, that's the plus positive moment. And over here you have negative moment, and it's because of the negative shear that you have at the end of your shear diagram. Question? I believe somebody has question.
Yes. After we do the shear diagram, can we use area to do the moment diagram?
That's exactly what I did. I use the area. You can either use
Okay.
the area or use the equation. So the area of this rectangle, what is the area of this rectangle? This rectangle, the first rectangle, 7.5 times 225, right?
Okay, yes.
Correct. That's exactly what we're doing.
Thank you.
No problem. So I got the maximum moment. And now I'm gonna work on the conjugate beam, but before I work on the conjugate beam, I have to go back and read the assumptions that we are making on the conjugate beam, or the instruction. There's one instruction over here, the second step says load the conjugate beam with M over EI diagram. So moment diagram over EI. So E is going to be calculated. So you don't know E right now. You don't know I. I mean, you know I, but I'm not going to enter the I to the diagram. I will only work with the moment. I is the moment of inertia, which is already calculated, 0.0814. Look at this beam right here, conjugate beam. The shear diagram has V, moment is M, and conjugate beam is M over EI. Conjugate beam is the same as the moment diagram, right? Conjugate beam is loaded with the moment diagram. Shape is the same. And you see that the maximum M over EI is 1,688 inch-pounds, which is the maximum moment over EI. E and I is constant, so they're not going to change. You will only enter them at the end of your calculations to calculate the deflection. Okay. So imagine you load this beam with the moment diagram. You will follow the same step. You will solve for the reactions. This RC, I call it RC1 and RC2 on my calculations. Since they are symmetric, this beam is symmetric, they will be the same. To calculate the conjugate beam reaction forces, you need to first calculate the areas. So you have a triangle and rectangle. So in the left side, if you cut this beam in the middle, center line, draw a center line, you see that you have one triangle with the base of 7.5 inches. Do you see this triangle?
Yes,
Your
sir.
base is 7.5 and your height is 1,688. So while I'm working out this, since I don't have the writing pad, it's better for you to work out this problem while I'm explaining. And ask me the question that doesn't make sense.
I hope this is not a stupid question to ask, but the stress and strain involving Hooke's law, will we have to include that by any chance
Well,
for any of the report?
that's the foundation of mechanics of materials. So I explained that before the midterm and during review session, Hooke's law, and you should know the Hooke's law before the final. That's for sure.
Absolutely, I do. I just wanted to make sure that that was on the final, you know, because you're taking some of the labs out. So that's,
Uh-huh.
you know, why I was asking. Thank you, though.
No problem. No problem. So in this first triangle, let's look at the area. Because area under this triangle, that's going to give me the load, applied load. Imagine treat this conjugate beam as a distributed load. When you have a distributed load along the beam, what do? How do you calculate the point load? So imagine you have a question on the final, you have a beam with the distributed load starting from 0 to 18 inches till the end of the beam, and the uniform load is 5 pounds per linear foot. To convert that distributed load to point load, you multiply whatever is the uniform, the distributed load, let's say 5 pounds per linear foot. And if the span is 18 inches, for example, 18 foot, you will multiply 5 by 18, and that's going to give you the point load, and that will be in the middle. 5 times 18 is 90. That's what we're doing over here. I'm converting this distributed load to a point load, so I can calculate for my reactions. Because if I know how much is the load is applied to this beam, I can solve for the reaction forces, because there has to be a reaction force same equal to and opposite to the applied load. So in the triangle, this is my equation, basically the area of the triangle. And in the middle portion, I have 1 and 2 rectangle. I'm only focusing on the left side. That's why I'm using 1.5. I'm looking at the only one section. Let me see if I can highlight this. Okay. I'm only working on this section, because whatever is the moment at this point, at 7.5, it will be the same moment at the 7.5 inches from the right end. So if I solve the left end, I can use the same numbers for the right end.
Are you solving it? Are you gonna put 3 point moments on there, or you're gonna try to make it in 2?
What do you mean 3 moment points?
Like, are you gonna, like, if I was doing this, I would have the triangle on the left. I
Okay.
would have done 7.5 and then like 1/3 or to get it in half.
Yes. Yeah, definitely. Definitely you're gonna use that. You have to use that because you have to find the center of gravity of the triangle, and that's gonna give you where the if the load is applied. When you convert that distributed load to a point load, where are you gonna place that load? It will go through the center of gravity, right? I know
Yeah.
exactly what you are trying to ask. Yes, definitely we will, next steps, you will see why we're gonna use that.
But I'm saying it looks like you're trying to do it in, because you're involving the other half of the rectangle. Like I would have done the
No,
triangle.
no, I did triangle first and then I did rectangle separate.
Oh, okay.
But if you separate them, that will be better. So center of gravity of the triangle, that's B/3, right? So applied load is the point load. It will be B/3. The distance will be B/3 from the right end. And 2B/3 from the left end. You will see when we get there.
Well, we have to know like all types of shapes along with their
Yeah,
inertias.
you don't have to know, but if you go back to your mechanics of materials book and you have the PDF version of it, you can see, I'm gonna show it to you right now, the index section or appendices, and you will see all the moment of inertia equations for specific shapes, for
Okay.
triangle and circle.
Yeah, I think the statics book has it too as well. I'll look at both of them, I guess.
Let me see. Think. So if you need it during the exam, you have the book PDF version over here. I'm sure at the end of the book, you will see that. Should be somewhere. Somewhere in there, and it's frozen. Anyway, you can use this mechanics of materials book and you can search for the center of gravity. And it should be all the way down. Try it. If you can't find it, Google it. Definitely, you will find a cheat sheet or PDF that shows all the moment of inertia calculations for certain shapes.
Are we allowed to use those on the final?
Well, since this is going to be take-home exam, I believe so. Because you will be by yourself, right?
Yes, sir. So yeah, we'll be able to use them.
Exactly.
Thank
Alright.
you.
No problem. Anyway, let's continue. We got the triangle, and then I'll get the rectangle portion. For the rectangle portion, I know my base is 1.5 and my height is 1,688 inch-pound over EI. So once I solve that, I know if I multiply by 2, that's going to give me the applied load throughout the beam. But if I only calculate the left section, that part is supported by the reaction force on the left end. So it will give me the reaction force on the left end, and it will be the same on the right end due to symmetry. It's already calculated 8,860 inch-cube pounds over EI. Now, you got this. Next thing is you will calculate the moment. Same way you calculate the moment over here, you follow the same strategy. Moment is the force times distance. Since you calculate the forces, the applied loads, and convert it to the point load, you can calculate the moment at any point along this conjugate. And that moment is going to give you the deflection. Let's see how we get it. I'm going to skip some of the sections over here because we already calculated most of the stuff. And one thing that I'm going to mention, I'm going to exclude one part from this. This is wrong information. Since this is not my handout, I was using one of my students just because it's clear, but this is not the way that you calculate the stress on the beam. And I will take it out before I upload the Moodle. Let's look at the shear and moment diagram. This is for 300 pounds. And let's go to conjugate beam. This is where we left off. He calculated the conjugate beam same way that is shown on the handout, which is the correct way. And once you get the reaction forces and the applied load as a point load after the conversion, it's time to take a moment about a point where you want to calculate deflection. So the first point, you use 6-inch. So the 6-inch moment, that will be the deflection on the real beam. For 300, that's what we are looking at right now. 0.093 and 300 pounds. When 300 pounds is applied, the observed data delta 6 deflection at 6 was 0.042. There is not too much difference, but let's see what is the difference. 0.042 and the calculated value is 0.0393. We have 6% error. Okay. So moment at 6. To calculate the moment at 6, you're gonna take a moment at 6-inch. And he's mentioning here the moment at 6 inches equal to deflection at 6-inch, correct? So we are assuming that counterclockwise is positive. First point load at 6-inch. What is the point load at 6-inch? That's 2700. And how we calculate it? That's 1/2 area of the rectangle. And then multiply by 2 inches. That's 1.5 plus 0.5 inches. Let me see. Let me see if he's making a mistake over here. Bear with me. I'm just looking at the paper, and I assume that it was correct. Let me do this calculation for a second. In the meantime, since I assume that you already draw the shear and moment diagram, and you already have the conjugate beam, try to calculate the moment at 6-inch. And I will do the calculation on my end. And I will check the numbers. So reaction force is 5,906.25 square pounds. Yeah. Let's look at this triangle first. That's 7.5. B over 3 and 2B over 3. 7.5 divided by 3 is 2.1. 2.5. Minus Check that. One point five. Let me see one thing. That's b over 3 and b, that's correct, b over 3. Mustan, we are looking at this one right now. Are you working it out? This center of gravity of the triangle? Because I'm trying to locate the point load on the triangle.
Yeah, I
Once I
got
get- Once I
two-
get the point load, what do you got? 2.5 and 5, right?
yeah 2.5 from the, if you go from the right
Yes.
line.
That's what I got, and I got 5 from the left hand. So that's where the load is applied, 5" from the left hand, correct?
Yeah, yes, sir.
That's what I did. And then you have a rectangle right there. That's 1.5. And if I'm trying to solve for 6, what I have 5, 6, and I have RC. That should be AL1, which is point load times 5, 7.5. 1. So distance from the applied load is 1 inches. Is that what you got, Rami? So this point load, he placed the point load on the wrong place. That's what I missed. That's what I'm seeing right now. The point load is not going to be at 6 inch, if I'm not mistaken.
I agree with that, but I didn't know how to go further than that. I have the 3-point loads, and I also have them facing down. Is it right that they're up?
No, this is correct. Yes, this is correct. This is your assumption. Yes, this is correct. But definitely this is not wrong. So I'll this is wrong. I will provide the correct solution for this one. This right section is correct, but left section, the way that he calculate the moment right here, that's not correct. The distance is not 2 inches. And what I was trying to do is to calculate the distance from that point where the load is applied in this triangle to a moment arm. So moment is at 6 inches. And we found that load is at 5 inches. 5 inches from the left hand. And it leaves me only 1 inch moment arm. So the PL point load, so he calculated 1 L times 6 inch, which is correct. 2,700 in square pounds divided by EI multiplied by 1. The first section will be, instead of 2 inches, that should be 1 inches. That's what I'm calculating right now, but I will check my calculation again. And if anybody did the calculation and got 1 inches, then I'm correct. And if I'm missing something, and if it's 2 inches, then let me know right now. If not, I will work it out and I'll post the correct one. So let's go forward. Let's go forward and complete this. This moment, at the end of this calculation, once you enter the E and I, you will get it. You will get the value in inches, and that will be the deflection. That's what he's doing over here. E, he calculated right up there from the equation that we saw here. Maximum bending stress over strain. Oops. So maximum bending stress, 1,125, and where he got that number is the maximum moment, 1,125. He gets the 1,125, put it in the equation. He knows the C, distance from the neutral axis to the top fiber, and we know the moment of inertia, and we also know the strain value from the experiment, 904.5. Let's see. That one was from different year, the numbers, but in this case, if we're working with 300, then we're going to use 921. But 921 is going to be divided by 1,000,000 because we are using the micro. So 921 times 10 to the negative 6 inch is what we're going to use if you are using the 300-pound loading scenario with the data given on the spreadsheet. Once you run the calculations, you will get your modulus of elasticity. Bring that elasticity all the way down here. And this calculation will give you the deflection at 6 inches. That's also equal to the deflection at on the real beam and the moment on the conjugate beam. That's the same computation. But like I said, I will look at this calculation one more time right here, how the way that he calculates the center of gravity and run the calculation, and then I will let you guys know. Then he's comparing the percent difference with the experimental, 0.041. That's the same thing that I did on the spreadsheet. The spreadsheet is 100% correct because I developed the spreadsheet, and I was looking for my own paper that I had my own calculation, but I couldn't find it. I left it at in my office. That's why I'm using this handout from my students' calculation. So conjugate beam is pretty much done, and I will get to the assignments. How you're gonna finish your assignments? Basically, you will follow the same steps that is shown on the handout. First one, and not this one, I will make it more clear, and you will run the same calculations. Only thing will be different is the loading. So you did 300 on this one, 450 on this one. That was the example, and you will use 150 pounds, and you will use the same equations. So the conjugate beam method was the complicated version, but that's what the report is asking for. You need to compare with the compare the result with the result from the conjugate beam, but there's easy way to calculate the deflection at any point along the beam. And this calculation, these equations are specifically for the simply supported beam with the loading scenario at 2 loads at equal distances from supports. Basically, it's symmetric. When you look at this free body diagram, you look at the free body diagram that's coming from your handout, that's the same. You can find the same same equations for different loading scenario and different orientation on steel manual. If you guys know or heard about steel manual before, it's like a steel manual deflection. Let's see. There you go. So I use one of those, whatever is corresponding to, or whatever is the same free body diagram as my beam. You gotta use those equations. This is for simple beam, uniformly distributed load. These equations, you can calculate the total equivalent uniform load, basically the applied uniform load multiplied by distance. That's what we use. That's what I was trying to explain before at the beginning of the class, how to convert from distributed load to a point load. Reaction force is the uniformly distributed load, W multiplied by L over 2. You can calculate the moment maximum moment, which is at the center with these equations. You can calculate the maximum moment, maximum deflection, my bad, maximum deflection with this equation. Let's see if this table has the same configuration that we are using. Symmetrically loaded beam. There you go.
Did you give us this equation?
Right here. Right here. So everybody can see this one. Simple beam, 2 equal concentrated loads. This is asymmetrically placed, but ours is symmetrically placed. Let's see.
Is this on our notes on Moodle?
There you go. 1 second, Austin. I will answer you.
I'm sorry, I didn't catch that.
1 second. This is our scenario. We have simple beam, 2 equal concentrated loads, P and T, and we have the reaction and reaction here. If you use these equations, you can calculate the total equivalent uniform load, A multiplied by P. In this case, your P is going to be either 75 or 150 or 225. And A is the 7.5. You can calculate the maximum moment, P over A, force times distance. You can calculate the maximum, you can calculate the moment at any point when X is less than A with this equation, P times X. And then if you want to calculate the maximum deflection, which is at the center, this is the equation that you're going to use. P times A, 24 EI. So everybody look at the screen for a second. So what do you see when you look at the equation? P times A divided by 24 EI. What did EI reminds you? M over EI, correct? So M over EI, M is the force times distance, P over A. So you can intuitively say that these equations are basically derived by using the conjugate beam method. Let's go back to conjugate beam method again. It says load the conjugate beam with the M over EI diagram. And then moments in the conjugate beam correspond to deflection in the real beam. Over here, to calculate the deflection, maximum deflection, you're using M over EI. The rest is just constant number. And this is the easiest way to calculate the deflection. So for your future references, instead of using conjugate beam method, you can pull up these tables and you can solve for deflection at any point. If you want to calculate deflection at x less than a was 7.5 in our case. For example, for 6-inch, you will use this equation, px over 6ei, and the parentheses 3la, whatever. I use these equations to check my calculations. So in the previous semester, I was solving these deflection on the board with the conjugate beam method. And then I was checking my numbers in the next lecture with the spreadsheet calculations. Because the spreadsheet never lies if it is constructed carefully. So at the end of my calculation on the conjugate beam, if delta 6 on 150 pound loading case is 0.0205, I come here, I change the loading P to 150. Automatically calculates the applied force at one location, right here at 75 pounds. And I have to enter some information, which is the span length, 18 inches overall. And I have to enter this 7.5, which corresponds to A, distance from one end to the applied force, 7.5. And it will calculate the maximum moment with the equation that's given right here. Moment max, F times A. So F is 75 times A, 7.5. I got 562.5. I can also check the calculation that one of my students did using this spreadsheet. That's which is what I'm going to do after the lecture. So now I'm at the maximum moment. I calculate that this section is solely for the moment of inertia calculation. Is highlighted section. I have to enter the base and height, and the C is going to be calculated based on the input data. And this moment of inertia is calculated using this section, base, height, data. This will stay the same because we're using the same beam throughout the experiment. Moment of inertia is going to be the same. Only thing will change is the loading. Maximum stress. I have my equation to calculate the maximum stress. I don't know if it's given here. No, that's not here. But you have the maximum bending stress equation on the handout. That's B24 moment max, 562.5 inch-pounds multiplied by C. C is the distance from neutral axis to the top fiber, we said, and divided by B30. What is the cell B30? B30, moment of inertia. That's the maximum stress. That's how we calculate the maximum bending stress. And MU is the strain gauge data. In this case, I entered 925, which was from previous one, but I had to change it to 481 because we are using the 150 pounds. So let's change it to 481. See, everything changed when I changed the strain gauge data. Also, it automatically calculates the strain based on the gauge data and converts it to micro strain, B29 times 10 to the negative 6, 0.00481. Then I can calculate the Young's modulus because I already know calculated the maximum bending stress, and I calculate the strain. Stress over strain is the Young's modulus. Here is the big equation. Deflection at 9 inches. Since you will have the spreadsheet, first develop your own and then check your calculation, check your spreadsheet using this one. Deflection at 9 inches. B21 times B23. Basically, this is the equation that I'm typing in this cell. F times A, force times distance, moment. So first is A right here, 7.5, and F is 75. And then I have 24 EI, that's right here, 24, B32 is E, and I is B30. Over here, this inside the parentheses, 3L squared minus 4A squared. L is B22. So all the information, all the input data is already in this table. And I put the equation for 4-inch as well. Let me change it to 4-inch. So here's the deal. Since 4 and 6 inches is less than 8, which is 7.5, I can use this equation for both scenarios to calculate the deflection at 6 and 4 inches. That's the equation that I'm using right here. F times X, B21 times here at 6. I think I play with this equation a little bit. Let me figure it out. 6 right here. F times X. X in this case, I'm solving for 4. I'm changing it to 4. Multiply by 3AL. 3 times A, 7.5 times B22 L minus 3A squared minus X squared. X is here 4, deflection at 4, and this 6 is constant, multiplied by E and I. That's 0.015.
Is that an X after F?
Which one? This one is X. F times X.
Thank you.
X can be 1, 2, 3, 4, 5, 6, up to 7.5.
It's just the distance, in other words.
It's a distance from one end to a point where you're trying to calculate deflection. If you're trying to calculate deflection at 3 inches, then X is going to be 3 inches. If you want to calculate deflection at 5 inches, then X is 5 inches. Make sense?
Yes, sir. I was just writing it down.
Okay. So let's see, based on this calculation, 0.024 is the deflection at 9 inches, right? That's 450 pounds. Let's go 0.024, the 150, there you go, 0.024. That's the observed data. Let's look at the 4 inches, 0.016. That's the observed data. Let's look at the calculation, 0.015. We're so close. So next, if I want to do 300, I change from 150 to 300. And the spreadsheet automatically is calculated, right? There are only a few things that I had to change it. One thing, it was the 300. The other one is going to be the strain gauge value right here, 481. So we're looking at the 300 pound right now. That's going to be 921. So everything is changed. All the calculations are run. 0.046 inches deflection in the middle. 0.046. And we got 0.074. It is a little bit off. But what about delta 4? The observed data was 0.031. Calculated data is 0.029, just pretty close. So what else I should mention in this case? Any question about this table and the spreadsheet calculation? Noah?
No, just the equation sheet that you showed us before. Are you gonna post that for us, or do we need that at all?
What equation sheet? This one?
Yes, sir, that one.
Well, this one I just pull up on Google. This is like general information. If you are a structural engineer trying to calculate deflection, just type deflection equations. This is gonna show up, and all you have to do, look at the beam you're designing, look at the orientation, and select your scenario. That's what I did. This is not on your handout.
Okay,
I just copy and paste from somewhere else this one, but this is the same thing. So wherever you go, doesn't matter what book you are using, you will see the same equations over and over. And this will be, since this is going to be on your handout, I mean on your Moodle, my bad, you're going to have this equation for simplicity for the beam and symmetrically loaded scenario.
okay.
Uh,
We can use the equation sheets that come out of our books for the statics and the mechanics and materials.
As long as you are following the conjugate beam method, you are fine. There are different ways to calculate the deflection. This is not the only way, okay?
Yeah.
I calculated
Right.
deflection using this equation with the conjugate beam. And this point I mentioned that this is the derivation of the conjugate beam. These equations are derived from conjugate beam. There are also different numerical methods. If the question statement asks you in the final exam, solve the problem, solve the deflections with the conjugate beam method, then you have to use the conjugate beam method. But if you read my email before class, I mentioned that I'm not gonna ask question. I'm not gonna make you guys responsible for the things that I haven't taught in class. This lab report and this handout specifically asking for conjugate beam. And if you see any deflection problem on the final, that will be related with the conjugate beam. That's what I'm saying. And you can also check your numbers from this spreadsheet. Let's say you calculate the deflection at 4 inches or 3 inches on the final exam, and you want to check your number, you want to check your calculation. You come here and change the loading scenario, whatever is given, let's say 500 pounds, automatically calculates everything, and you get your deflection. And if this deflection is the same as what you calculate on your exam, then it's right. You got it correct. Okay, I believe this spreadsheet is clear. And I will clean this out and I will provide a better solution. What else? Don't take in this one into consideration, since I'm not required in a lab report. This was the guidelines that I provide usually. You're not required to do the lab report. You will just provide the calculations. And that's going to be for 150 pounds. And you will calculate the deflection at 9, 6, and 4 inches and compare with the observations. Once you finish that, you are done with the beam bend. And this is going to be due before the final exam. So before you take the final, you should submit your beam bending, or if you have any other report remaining for unsubmitted. Column buckling. That's 7 right now. I don't want to get into column buckling. Before our next class, make sure you watch these videos. I have one, this should be from my lecture last year. At least you have an understanding on column buckling before you come to class. Over here, I go over the theory and the equations and also calculations, similar to what we have been doing from the beginning. You will understand how to develop the tables, how to write the equations, etc. And when we are in the class, I will just go over the theory and do similar calculations and talk about the final more. Then next week we can have the final following week. So today is 27th, 4th is gonna be the last week. And the 11th, I will check the academic calendar again and see when is the final exam week. And if you guys have, let's say it this way,
Concrete
I
says
don't
it's
know,
due on 11th.
what is it?
I'm sorry, the concrete lab report, it says that it's due on the 11th on the final. I guess that would be the day.
Okay, and that will be the final exam day. I think when I was doing the concrete, when I was doing the due dates, I entered the final exam day. But I will check the calendar again. I will let you guys know when is the final exam day. It doesn't have to be specific day, like we don't have to stress about it. I will make it in a day that you guys are not overwhelmed with the other final exams. 'Cause
But concrete
I
is still
remember-
gonna be, concrete is still gonna be due on the 11th, though.
Yes, that's what I said 5 minutes
Okay.
ago. If you have a remaining report that you haven't submitted yet, all the reports are due before the final exam. If final exam on the 11th, then on 11th. If it's on 13th, then it's on 13th. Okay? That's, I believe that's gonna help. Okay?
And I just want to make sure of one thing. So you said that we have, like, when I was looking over your email from earlier, that we have a handout that we have to, like, fill out and do before the end of the, like, before the final. Is that on Moodle already?
Let's go to email again.
The tensile one that you said, that was worth extra points.
No, not that one. It was I'll just wait till he gets to the email.
1 second. There you go. I say there will not be an assigned lab report on the beam bending and column buckling. Instead, I will give you a worksheet
Yes.
to solve and submit it before the final exam. So the worksheet is basically those handouts that I gave right here. This handout, it's a worksheet. You have the data, you have the equations, and I went over the calculations, and I provide the spreadsheet as well to check your number calculations.
Yes.
And first, we did the 450 pound loading scenario right here. And then we did 300s, which was a little bit rough to go over. I'll make it clear more.
And
Yeah.
so we have to solve for 150.
Exactly.
Okay.
Yes,
I just
yeah.
wanted to make sure of that.
Okay, so 150 pounds. You will solve for 150 pounds at 3 different locations, Delta 9, Delta 6, and Delta 4. Same way. Okay, Delta 9, which is Delta Max, you can just enter it over here and see it. 150 pounds, for example. I did it just like 15 minutes ago. 481 again, 481. There you go, 0.024, 0.015, 0.024, and 0.016 is here, and I got 15. So this is observed, this is real. Like, and this is observed, and this is the, sorry, this table is the calculated one, data.
So essentially, everything is due on the 11th of the final.
Right,
Okay, thank you.
no problem. What else about this assignments? Anyone has question about the assignments on this one? Basically, I don't know how this student got that the report or the calculation that I was showing. It just looked clear to me that that's why I picked that one. But obviously there are mistakes on this one. Not this. I just close it. So you will have your moment shear diagram, have the conjugate beam diagram, and solve for the moment on the conjugate beam. And that moment is going to give you your deflection at delta 9, delta 6, and delta 4. And if you're concerned about your results, let's say your deflection is way off than observed, just go back to spreadsheet, enter your data to the spreadsheet, check your spreadsheet results, deflections with the calculated ones. And then if you're still confused, just give me a call. And then we can find a solution.
And you said this spreadsheet you're looking at right now is on Moodle? Because I actually don't see it.
Yes, you don't see it. I said I will put it on.
I
Moodle.
don't see it either.
Yes, let me put it on Moodle. I said I will.
Oh, sorry, my bad.
Let's do it.
Yeah, I was looking just to make sure because it's obviously easier to ask you about it, you know, while we're in
Right.
class than over email.
Definitely.
Professor, I have to go break my fast. It's almost time.
Yes, go ahead, man. You deserve it.
Master man.
All right.
Thank you.
All right. All right, let's save this to. Okay, this one is done. So you got the spreadsheet. You don't have the other sample calculation because I don't believe that it's 100% correct. So I will make it correction. And I will upload the sample calculation as well. But in the meantime, I'm sure everybody is comfortable with the moment and shear diagram, and you can just develop that conjugate beam diagram, since this is the same as the moment diagram, and work it out till you're waiting for my correction. That's it from me today regarding the beam bending. And like I say, we work on the column buckling as well before next lecture. It's going to make everything smooth. And this way I can have more time to work on the final exam, like review the final exam.
Thank you, sir.
Conjugate beam is important. You will see a problem 100% on conjugate beam. You will solve for deflection at any point. Okay. That's it from today. It was nice seeing you guys. And
Thank you so much.
You're welcome. You're welcome. You guys have a good night.
Have a good night, sir.
You too. Bye-bye.
Thank you.
You too.
Thank you.